Section: Introduction. In this section, we introduce in-context learning, ICL, a powerful approach in natural language processing, NLP, that allows us to use a large language model, LLM, with a set of input-output examples to tackle various tasks. However, we face limitations with ICL, particularly regarding the maximum number of examples we can use due to the model's context length. The effectiveness of ICL can also vary based on the chosen examples. Currently, methods for selecting these examples are mostly heuristic and do not effectively measure how each example impacts the model's ability to generalize. Often, we select examples randomly or based on simple criteria, which can lead to less than optimal results. This raises the question: are all examples useful, or are some just noise? Can we automate the process of distinguishing between them? To address these issues, we propose a new method called Mixtures of In-Context Learners, MOICL. This method allows us to learn how different sets of examples contribute to the prediction task dynamically. MOICL prompts the LLM with various subsets of examples and combines their predictions using a weighting function that we can train through optimization techniques. We analyze how MOICL performs in different scenarios, including when some examples are incorrect. Our findings show that MOICL consistently yields more accurate results than traditional ICL. Additionally, MOICL does not require access to the internal workings of the LLM, making it suitable for black box models. It also alleviates complexity issues related to self-attention, as it distributes training samples among multiple experts. We can further enhance the method's efficiency by simplifying the mixing weights. In summary, we present MOICL, which assigns weights to subsets of demonstrations and learns from them, identifying the best and worst contributors through optimization. We demonstrate that MOICL competes well with standard ICL while being more efficient in terms of data, memory, and computation. It also shows resilience against noisy examples and imbalanced labels. We define our approach by partitioning the set of demonstrations into several subsets, which we refer to as experts. Each expert is evaluated alongside the input text, and we combine their predictions using a vector of mixing weights. We explore different methods for calculating these weights, including using trainable parameters or a hypernetwork that generates weights based on all demonstration subsets. This flexibility allows us to adapt to unseen examples during training, enhancing the model's performance. Section Summary. In this section, we introduce Mixtures of In-Context Learners, MOICL, a method that enhances in-context learning by dynamically weighting subsets of demonstrations to improve prediction accuracy and efficiency, particularly in the presence of noisy or irrelevant examples. MOICL allows for better generalization without requiring access to the internal parameters of the language model, addressing the limitations of traditional in-context learning approaches. Section: Sparsifying the mixture weights. In this section, we address the challenge of needing to call the base LLM multiple times for each token in MOICL, which can be inefficient. To improve this, we propose to simplify the mixture weights so that only a smaller number of them are active. We define the output of our weighting function using a set of weights for the experts and a masking function that selects the top weights. To train our model effectively, we utilize a method called implicit maximum likelihood estimation, which helps us backpropagate through the selection process. For our experiments, we primarily use the Llama 3-8B model and its instruction-tuned version for classification tasks, while the base Llama 3-8B is used for open-ended generation tasks. We also explore the impact of different model sizes using Llama 2 chat models. To evaluate MOICL's performance on classification tasks, we use several datasets, including tweet-eval and SST2, reporting results on the development set. For generation tasks, we utilize the natural questions dataset in an open book format. We compare MOICL against several baselines, including the standard concatenation method, which combines all demonstrations into one input, and a random search approach that samples subsets of demonstrations. We also consider ensemble-based methods and fine-tuning techniques like LoRa, which requires access to model weights. Additionally, we analyze a version of MOICL that treats all experts equally. For evaluation, we measure accuracy for classification tasks and use exact match for generation tasks. We provide further details on our experimental setup in the appendix and confirm that our method's performance is stable across different partitioning methods. In our experiments, we aim to answer whether MOICL shows improved general performance compared to traditional concatenation-based methods. Section Summary. In this section, we address the limitation of MOICL requiring multiple invocations of the base LLM by proposing a method to sparsify the mixture weights, allowing only a subset of experts to be activated. We detail our experimental setup using various llama models and datasets for classification and generation tasks, while comparing MOICL against several baselines and evaluating performance through accuracy and exact match metrics. Section: MOICL in classification tasks. In this section, we evaluate the effectiveness of MOICL across different datasets by comparing it with baseline methods. We set the total number of demonstrations to 30 and varied the number of subsets to 5, 10, and 30. Our results show that MOICL outperformed the baseline ICL on datasets like offensive, hate, fever, pause, and QNLI. However, in the cases of SST2 and RTE, MOICL performed similarly to concat-based ICL in SST2 but showed lower performance in RTE. Notably, MOICL scalar achieved the best results with 10 or 30 subsets, significantly improving performance compared to concat-based ICL, except for SST2 and RTE. This indicates that MOICL effectively balances efficiency and effectiveness, even as a larger number of subsets reduces context length. Next, we examine the impact of partitioning size on performance using the tweet-eval offensive test set. With a fixed total of 30 demonstrations, each subset contained a varying number of demonstrations based on the number of subsets. We found that with uniform weights, performance declined as the number of demonstrations per subset decreased, which is expected. In contrast, with scalar, performance increased, likely due to the added flexibility from having more subsets with tuned weights. We also explored the effect of allowing negative weights for experts, treating them as potential anti-experts. Our findings showed that restricting weights to be positive significantly degraded performance, as some demonstrations can be beneficial when used as anti-experts. This insight helps us better understand the usefulness of experts in our model. Furthermore, we investigated how MOICL handles out-of-domain demonstrations by associating weights with each expert. Our analysis revealed that as the proportion of out-of-domain demonstrations increased, standard ICL methods struggled, while MOICL effectively reduced their negative impact. We observed that in-domain demonstrations generally received positive weights, while out-of-domain demonstrations tended to receive negative weights, confirming that our method successfully mitigates the influence of out-of-domain data. Lastly, we assessed our method's ability to manage label imbalance using the tweet-eval offensive dataset, where we set up 29 offensive and 1 non-offensive demonstration. Given the dataset's label ratio, this imbalance could harm performance. Our results indicated that standard ICL methods suffered a significant drop in performance due to this imbalance, while our proposed method, scalar, showed the least performance decline, effectively addressing the label imbalance issue. Section Summary. In this section, we demonstrate that MOICL outperforms baseline methods on various datasets, particularly excelling with larger subsets, while also effectively managing out-of-domain demonstrations and label imbalances by assigning appropriate weights to experts, including the use of anti-experts. Our findings indicate that MOICL's flexibility and efficiency contribute to its superior performance, even in challenging scenarios. Section: Filtering noisy demonstrations. In this section, we explore how assigning weights to demonstrations helps us manage low-quality or noisy demonstrations. To test this, We created noisy demonstrations in NQOpen by randomly altering answers among a few options, resulting in a total of 12 demonstrations. Our findings indicate that our method effectively deals with noise. While the performance of the concat-based ICL drops significantly with more noisy demonstrations, the MOICL methods maintain their performance. When we do not adjust the weights, performance declines as noise increases, but with tuning, it remains stable, showing over a 35% improvement with 10 noisy demonstrations. This is evident in the learned weights, where we see a clear distinction between normal and noisy demonstration weights. Next, we analyze the effect of reducing the mixture weights in MOICL. We refer to the subsets with the largest weights and compare them to a method that uses a mask. Although MOICL scalar achieves the highest accuracy, it requires learning weights for each combination, making it more practical to select a few from a larger set. The method using a mask shows stable performance, especially with fewer demonstrations. We also discuss the generalization to unseen demonstrations. While the scalar method is simpler, it has the limitation of needing a fixed set of subsets. To address this, we propose using a smaller hypernetwork to calculate weights for any demonstration subset. Our comparison shows that the hypernetwork can generalize well to unseen demonstrations. Considering the trend of increasing model sizes, we examine how our method performs with different sizes of Llama 2 chat models. We find that MOICL consistently outperforms concat-based ICL across all sizes. We also look at the size of the hypernetwork and find that even a small model performs well, leading us to choose T5 small as our hypernetwork. Lastly, we address the data and compute efficiency of MOICL. We analyze its performance with limited training instances and find that it is highly data efficient, outperforming concat-based ICL with fewer annotated demonstrations. Additionally, we compare the average inference time and find that MOICL is not only more accurate but also more time efficient than concat-based ICL under the same conditions. Section Summary. In this section, we demonstrate that our method effectively manages noisy demonstrations by assigning weights, maintaining performance even as noise increases, unlike concat-based ICL. We also explore the impact of demonstration subset selection, model size, and data efficiency, showing that our approach consistently outperforms alternatives while being both data and time efficient. Section: Complexity. In this section, we discuss the complexity of our proposed MOICL method, which divides demonstrations into subsets instead of simply combining them. This strategy helps to shorten the input context length for large language models, LLMs, which is important because the computational demands of transformer-based architectures grow significantly as the context length increases. We analyze the computation costs associated with LLMs and hypernetworks, denoted as C_LLM and C_hyper. The traditional concatenation method for in-context learning, ICL, incurs the highest cost since it combines all demonstrations with the test input. In contrast, the ensemble-based ICL method has the lowest cost by pairing each demonstration with the test input. Our MOICL method falls in between, with costs influenced by the number of subsets, K. The hypernetwork processes all subsets to generate weights, adding a cost that scales with the square of the number of demonstrations. However, since C_LLM is typically much larger than C_hyper, our approach remains computationally efficient. Additionally, the weights for the subsets are calculated just once and can be reused, making the initial computation a one-time expense. We also explore in-context learning, ICL, which is a few-shot learning technique that involves providing training examples as input to the model before the test example. This capability is becoming more prevalent in large models like GPT-3 and PaLM. While more demonstrations generally improve task accuracy, we find that after a certain point, adding more examples can lead to diminishing returns or even reduced accuracy. Moreover, in transformer-based LLMs, increasing the number of ICL demonstrations can be computationally intensive due to the quadratic growth of self-attention operations with context size. ICL is also sensitive to out-of-domain examples and label imbalances, highlighting the need for careful selection of demonstrations. We introduce ensemble-based demonstrations as an alternative to the concatenation method, where each demonstration is provided to the language model alongside the input to generate a next token distribution. These distributions are then combined using a product of experts approach to create the final output. We propose mixtures of in-context experts for tasks like anaphora resolution, where we calculate expert weights based on the similarity between the test input and demonstrations. Our work extends these models by examining how merging expert activations at different stages affects both efficiency and task performance. Our mixture of in-context learners, MOICL, builds on this by learning a weighting function that assigns specific weights to each expert, allowing us to address various challenges in ICL without needing access to the model weights.